This example is the inclusion formation during the solidification of the steel. So when you actually solidify the steel, the remaining oxygen and sulfur and some other species can react with the solute element to form the oxide or nitride and sulfide inclusion during the solidification of the steel. And also, while you actually have the solid state phase transformation, this kind of inclusion can be further change its phase to the some other actually the compound and the solution phase. Okay, so this kind of the inclusion especially is very interestingly applied in the so-called oxide metallurgy concept. So, for example, as you can see here, there's the small actually the black particle here, and along the actually the black particle around the black particle there was the acicular ferrite is formed. And if you actually zoom up this one, you can see that there's the particle inclusion here, and then around here there's the nucleation of the acicular ferrite. And so this kind of the inclusion, some special inclusion with a special chemistry, can accelerate, can be utilized as a nucleation site for the acicular ferrite. So this is the so-called oxide metallurgy. And so people want to utilize the inclusion for something more beneficial effect instead of the inclusion as a defect actually site. That's why we call it oxide metallurgy. And one of the most famous actual application is this kind of acicular ferrite formation. So let's look at some of the application for this kind of the oxide metallurgy. So this is the series of the experiment carried out by the Professor Hagen-Lee's group in the GIBT in post-tech Korea. They they changed actually the chemical composition of the solute and adding the different kinds of solute element and to find out what kind of inclusion can be formed depending on the solute composition. So this is the one of the inclusion they found by changing the Mn and Si ratio in the molten steel. And after actually the casting, they found this kind of the Mn-Si oxide with some Mns actually formation. So there's certain amount of sulfur here too. And then when they add the titanium on top of that, they can see the modification of this Mn-Si oxide to the Mn titanium oxide. And then you can see the change of the morphology as well. And then in the end, when you add more and more titanium, the Mn titanium oxide become completely titanium oxide. Okay. And then after that, they try to add some additional amount of magnesium. And then they see also modification of this titanium or Mn titanium oxide to the MnMg, so titanium, magnesium, manganese, and oxide actually inclusion. And eventually, if you add too much magnesium, then it will be only magnesium oxide. And then among this one, among the certain ratio, they start to add additional aluminum, and then they see also change of the morphology. So there's so at least there's the 1, 2, 3, 4, 5 elements you are changing with sulfur and then nitrogen and oxygen on top of that. Okay, so even you pick all the 3 elements, sulfur, oxygen, nitrogen, there's the 5 species, 5 element is changing. So even you change it about the 10 actually different the composition of each element. So 10 times 5. So it will be about 0.1, about 100,000 actually possible case you have to study. And of course, I mean, if you have enough time and enough money, you can do this kind of experiment, but realistically, this is impossible. So one of the way actually you can do this kind of research is thermodynamic calculation. Of course, you have to validate your thermodynamic calculation first against your experimental data, and then if your calculation is reasonably good, then you can utilize this kind of thermodynamic calculation and to find out the change of the different kinds of chemistry depending on your alloy composition. And that's what we have done actually over the series of the experiment here. And then we proved that thermodynamic calculation is very useful for the inclusion calculation, especially for this kind of the oxide metallurgy application. So you can see the series of the paper from the Hagen-Riss group and then find the comparison between the experimental data and the thermodynamic data if you like. And so this is also another morphology change with the addition of MgO. And then here you can see actually the thermodynamic calculation result against the experimental data. And this was very well matched with experimental data. As one of the example, let's try to do the this calculation. So in this one, I mean, I don't know whether you can see it well. So there's the iron and then 0.1% of carbon, 1.5% of manganese, 0.1% of silicon, and then small amount of titanium, oxygen, and the sulfur. And we want to do the calculation of the inclusion during the solidification of the steel and even in the solid state of the steel. So you need a steel database because we are going to do the solidification and the solid state steel. So we need definitely steel database, and also we need oxide database. And if it is necessary, we can even use the packed PS database. So at least we need FT oxide and FS steel database in this case. And some of you may ask me, can you use the FELQ database instead of the FS steel database? Yes, you can use it if it is only in the liquid state, but you have to consider both liquid and the solid actual transformation. So it's better to use the FS steel database in this case. So let's try to do the real calculation by using the PackSage. So in order to this calculation, you have to open Eclipse program, and then you have to enter all the element of your steel. So for example, here I already set up actually those input condition. So we have 0.1% of the carbon and 1.5% of manganese, 0.1% of silicon, and 0.0061% of titanium. It's very small. And then we have the 0.01% of oxygen and then 0.007% of sulfur. And sometimes it's very difficult to actually calculate what's the remaining amount of iron. So then you can do the question and then space 100. Then it will give you the exact amount of iron to make the all together to become 100. Okay. And of course, the unit in this case is in gram because this is weight percent. And then I'm using the Celsius temperature in Celsius. Okay. And then database, as I mentioned before, I prefer FS steel database and FT oxide database. And if you want to, you can even include the packed PS database. Okay. And then next, then we are going to select all the possible pages. So select all solution page from the FS steel database and also FT oxide database. And then all the solid page as well. And of course, in this case, there's no gases forming, so I'm not taking it. But if you want to, you can also choose this one. And the range of temperature here is set from the 1000 degrees Celsius space, 1600 degrees Celsius space, 10 degree. So we are doing 1000 to 600 degrees Celsius every 10 degree. And instead of only taking the normal calculation, I'm taking normal and the transition. So when you click typically normal and transition, PackSage will do the calculation every 10 degrees Celsius. And then between the previous calculation and the next calculation, if there's any phase transformation, then PackSage notice that phase transformation, and then it tries to even calculate exact phase transformation temperature. That's the meaning of transition. Okay. So eventually it will have the more than 61 calculation, but we don't know how many more. So 61 plus calculation is required in this case. Okay, so everything set up, then you can run the calculation. Then in a few seconds, you can see the actual result in the most of the time. So it's coming. It actually take more than few seconds. I'm sorry. But this is reasonably fast enough. So we have the 1000 degree, 1100 degree. So for example, let's go to this 1160, and then there's some transition here, and then something else. So there's something happening here. So 1160, if you look at, there's 99 gram of the FCC, and as I mentioned, this is all modeling species. So you don't have to worry about that. There's titanium carbide in the FCC phase. And as I mentioned, this is model species in the fact phase. But if you want to really know what's the FCC composition, then you have to look at this composition, system component. So here you have carbon, for example, this one, 0.01% basically. And then there's some other species as well. And then you'll have this amount of the MES. So it's MNS actually the kind of the phase. And then you have this amount of the ilmenite phase and this amount of rhodonite phase. It's very complex, yeah. And then if you go probably 1170, there might be some difference. So there's the FCC phase and slag phase. Okay, so there was no slag below, and at this temperature, we still have the liquid slag phase. And if you look at the actual slag component here, it's mainly MnO and then SiO2 with some titanium oxide and some sulfide actually. So that's the main component of the slag phase. And so that's why there was transition. Okay, so if you look at actually there's two transitions. So if you look at it, there's some more actually the change than actually slag. Okay, so it's good. And let's assume we checked all the data, and then we can try to plot the result. So go output and plot, and then plot the result. So first one I want to do is I want to see the overview of the entire actually the phase. So I'll take the axis and then y-axis. So can you see it? Y-axis, and then I'll take the gram, and then it's very strange. It's log scale. Then if you don't want to log scale, you can just use the linear scale like this. So 0 to 100 for the gram. So gram of the certain phase, and then temperature, refresh, then it will set up actually the prop range. And then you go to the select. So I say gram, so you have to say that gram of what. So select. And then there's the many phase, but in general, if you want to select all the phase which is stable in the calculation, which means you have the more than zero amount of the value, then you can go select all stable phases. And this way, you can say that there's the 14 species have the more than zero amount, and then say OK, and then plot. Then you can see all the result by one shot. So here, as you see, x-axis is temperature, y-axis in gram, and there's the three main phase. So first one, let's look at it. If you click here, you can see the name. So this is liquid phase, and then BCC phase, and then this is FCC phase. So there's the phase transformation, liquid to the BCC, and then just at the end of the solidification, you are transforming to the FCC phase. So this is the overview. But there's actually small thing in the bottom. You cannot see very well here, but there's something, okay? So you can zoom in this area here. So let's just double click outside of your axis, okay? And then now you can set actually your y-axis range from 0 to 100 instead of that 0 to 0.06, because I know the answer, so just follow me, 0 to 0.06, and then every 0.01, for example, and 0.01. So this will be good axis. And then say OK. Then you see that there's something popping up. So this one, you see it's a slag. In this case, you can say that this is the liquid inclusion. And then this is MS. That was the MNS kind of the inclusion, as you've seen before. And here you have the pseudo. This is the PSU is the pseudobrookite, I'm sorry. And then this one is ilmenite phase. and this one is the rhodonite phase. So there's many different phases forming. So at least you can see that there's liquid phase formation, liquid inclusion formation from to here to here. Okay, so if you want to label all this phase, then you can just simply go and click the actually button, and then T, add label, and then you can add one by one. And if you want to modify the actual name and the angle and the size, you can do it. You can do it whatever you like. Okay, so all this one. Okay, so that's good. And then probably you may say that, okay, I want to see even the composition of the slag phase. Okay, then we can plot the composition of your slag phase, liquid inclusion phase, basically. So let's just close this one, exit. No, I don't want to save it. And then you can go to your axis again. And then instead of gram, now I want to take it weight percent. Can you see it? So variable weight percent. Okay, and say refresh and okay. And now you have to go to select what kind of the weight percent you want to select. Okay, so there was the 14 species was previously selected. It's not deleted yet, so you have to make it clear. And then you have to now go down to select what kind of species you want to plot. Okay, so if you go down, this is the all species inside of solution, FCC and BCC and BCC B2 and all the thing one by one. And if you go further down, now we can start to see the slag. Okay, slag number 1. So if you want to see actually all the species in terms of modeling species like this, you can click all this one, for example. Then we can see that there's the usual oxide phase, and then also there's some special sulfide phase. And so SiS2, I mean, theoretically, this is not existing, but from the thermodynamic model point of view, we're actually considering this kind of species. And so you can actually plot in this way. Or if you don't like it, you can save all this result as Excel file, and then you can regenerate actually the amount of the oxide and the sulfide by yourself. Or if you go to the very end of this result here, then you can see the elemental, actually the species. So it's like iron, manganese. So for example, in the slag phase, so let's go down, keep going down. Here, slag phase, you can actually plot it as iron metal, iron actually the amount, manganese amount, titanium amount, sulfur amount, silicon amount, oxygen, carbon, and in this way. So this is also another way to plot it as element. But the element is not very, I mean, we don't use the element when you plot the composition of the slag that much here. So this is not the best choice. So the best choice is the slag component I selected before, but the sum of the slag component like SiS2 or TiS2 and this kind of slag component is a little bit weird, a little bit not actually well actually done used in the slag community. So you can actually save all those results as Excel file, and then you can regenerate the amount of each different phase, and then you can assume that all the sulfur is, for example, as MNS, for example, and then you can replot it by yourself if you like. But anyway, at the moment, we select all those slag species, and then we can say okay, and then let's look at the result. So this is the result. Okay, so this is the change of the composition. So we know that the slag was disappeared at around this temperature. Yeah. So all the rest here is just meaningless. So only the information among in this area is actually the good information we need for our actually the calculation. Okay, so we can do this kind of the weight percent calculation for the slag component too. Okay, that's good. And so you can do the similar kind of the inclusion calculation during the solidification of the steel, and also you can do of course, in the liquid steel itself too. Okay, so if you have any other question, you can also contact me anytime. Thank you very much.